Sections 5.4 and 5.5 are combined together since they're kind of short. And the first thing in 5.4, which is kind of a review thing, is how to simplify an expression with a rational exponent. And you don't have to do it in this order necessarily. There are going to be cases certainly where you could go the other way, where you would have a to the m and then to take the nth root of that, where that might be simpler. But I tend to do it this way because it keeps the number smaller. So if you do a to the m first and then take the root, usually you get a bigger number that way. And I thought if I keep them smaller, then you get to use more squares that you know off the top of your head and things like that. So that's my personal strategy. I guess you don't really have to follow it, but that's why in all these I do the root first. So like here, I've got 27 to the 2/3. I'm going to raise 27 to the 1/3 first. Now whatever that is, which is 3, all right, that's the cube root of 27, then I'm going to square it. So that's basically what I did. I said, all right, this is 3. You square 3, you get 9. Here, I guess here you got to be careful because that negative is out front, right? It's not negative 16 all raised to the 3/2. It's the negation of 16 to the 3/2, right? No parentheses around this. So you just have to handle the 16 to the 3/2 and just keep the negative out front the whole time. So I rewrote it so I'd be doing the root first. And 16 to the 1/2 power, that's the square root of 16, which is 4. And then 4 cubed is 64, so the answer is negative 64. This one's got a negative exponent, so I rewrote it with a positive exponent first by putting it in the denominator. And then I did what I always do. I did the root first, and I said, all right, 25 to the 1/2 power. That's a square root of 25, so it's 5. Cube it, 125. So the answer is 1 over 125. Another thing that comes in handy, and this is probably also kind of a review topic, is how to rewrite radicals with exponents. Basically how to go back and forth between radical notation and exponent notation. So like how the square root is the same thing as raising x to the 1/2, or the cube root is the same thing as raising x to the 1/3. Right? Those are kind of the common ones, but you can have it with 5th roots and 10th roots and whatever as well. So first one, the square root of x plus 1, you could write that as x plus 1 in parentheses, so that whole quantity raised to the 1/2 power, right? And it's that theme. So like here, same kind of idea where you say, well, that cube root of y, that's y to the 1/3, so we can rewrite that. And then here you have a power raised to another power, so you can multiply them together. So you get y raised to the power of negative 5/3. But then to rewrite that with a positive exponent, you got to do this and bring it down to the denominator and write it as 1 over y to the 5/3. Let's see, here to combine this into a single expression rather than a product, that's x to the 1/2, since it's a square root, and that's a 4th root, so it's x to the 1/4. And that's what I've got here, x to the 1/2 times x to the 1/4. And when you have two expressions like this with the same base being multiplied together, you can add the exponents, which I did here, and I said, okay, well, I can make that look better because I can get a common denominator and say that's 2/4 plus 1/4, so that's 3/4 up there in the exponent, and that's the simplified version of that one. The domain of a root function. Most people have a concept of this already, where usually that concept is something to the effect of that you can't have a negative under the radical. That's true when it's a square root. And since usually you deal with square roots, then in that case that does work. It's also true for any other even root. However, you can take an odd root of a negative, right? Like the cube root of negative 8 is negative 2. That actually works. Or the cube root of negative 27 is negative 3, right? That kind of thing. So really what you end up with is that in even roots, or with even roots, that's where you got to watch out. You don't want to take an even root of a negative. That's not going to work. That's not going to be a defined expression. At least not with real numbers, right? You can say, well, what about complex numbers? But we're not dealing with those for the moment. But with odd roots, anything goes, right? If you have the odd root of an odd number, that just means that when you take that root, you get an odd number. So the odd roots are easy because the answer is always everything works. So let's see. We want to get the domain of these functions here. Well, this is a square root, which is even, right? That's a second root. 2 is an even number. So you need the thing under the radical, the radicand, to be non-negative or greater than or equal to 0, right? The way that you would probably usually say that. So then we just have to solve this thing, subtract, or I guess add 18 to both sides. You end up here, divide both sides by 3, end up there. Okay, so you need x to be at least 6 or greater than or equal to 6. So the domain should be from 6 to infinity and include the 6 because it's a greater than or equal to, right? So that one's not so bad. And number 8 is also an even root, right? It's a fourth root. That negative out front doesn't really matter for what we're trying to do here. So we just need to worry about what's under the radical. We need that to not be negative. So we need 10 minus 2x to be greater than or equal to 0. You subtract 10 from both sides, you end up here. But to get x by itself, you got to divide by negative 2. And since we're dividing by a negative, that's going to flip the direction of the inequality. Right? That's why I stuck this one in here, because there's that old thing that we haven't talked about in a while, but it sort of comes back here every once in a while with this sort of thing. So yeah, you divide by a negative 2, it's going to reverse the direction of the inequality. So it should be x less than or equal to 5. So like this as an interval, right? Less than or equal to 5. So including the 5, you want to bracket around the 5. Then number 9, that's the best. Odd root, you don't really have to do anything, right? No restrictions with an odd root, right? It's a cube root. So everything goes, the domain's all real numbers from negative infinity to positive infinity. There's not really any work. Number 10 kind of makes up for not having any work in number 9 though. It's a square root, so you need the thing under the radical to not be negative. So you need 81 minus x squared to be greater than or equal to 0. And then if you factor it, you end up here. And then I guess if you want to do it with the corresponding equation, I wrote it up that way like in chapter 4, where then you'd say, okay, well, if x is 9 or if x is negative 9, then you're going to get 0 on the left side. So those are the numbers that are going to break up the number line. You just have to check those 3 intervals. So I used 0 for the middle, and that was positive, right? Because you're going to get, clearly, if you look up here, it's going to be 81. And then on the 2 ends, I used 10, and then I used a negative 10. Those both end up being negative. But we need 81 minus x squared to be greater than or equal to 0. So we need where the plus is. But since it's greater than or equal to, the endpoints are both okay because they both give you 0. So we're going to include both of them. So we've got the closed interval, right? That's why we got the brackets from negative 9 to positive 9. Then for what we're going to cover in section 5.5, equations involving roots, the best thing I think I can say for the equations involving roots, as far as how you would solve one, is get rid of the root. I mean, I guess first you have to get the root by itself, then get rid of it. So the way you get rid of it is just by raising it to an appropriate power that would ultimately give you an exponent of 1. So like if you have a square root, if you square that, then the power that you're ultimately going to end up with is 1/2 times 2, which is 1. Or if you have, let's say, a fifth root, then if you raise that expression to the 5th power, then ultimately your exponent's 1/5 times 5, which is 1. So that's basically what the strategy is here. The one other thing, and I should point this out, even though it's in bold and underlined, is you've got to check the solutions here, because with roots, weird things can happen. Realistically, you just have to worry about even roots. If you have odd roots, this won't happen. And this goes along with how with odd roots, you don't have any domain restrictions or anything. But also, anything with an odd root is 1-to-1, and that's the real reason why you don't have to check it. But you do with even roots. So for a lot of people, it just feels easier to be safe and check all roots, and that's totally fine. But here we're going to have to. It's an even root. So we've got this. We've got this equation right here. The root's already by itself on the right. And it's a square root. So what I'm going to do to get rid of that root is I'm going to square both sides. So if you square both sides, then on the right side, you've got the square root squared. So that's really just 5x minus 1. On the left side, I expanded this out. So I squared that binomial, x minus 5, and you get x squared minus 10x plus 25. Then this is a polynomial equation. So I just got a 0 on one side. And then I said, oh, look, this factors because negative 13 times negative 2 is 26. And those numbers add up to negative 15. So yeah, this is going to factor. And then we get that x equals 13 and x equals 2. But we got to check them. So if we check them, it looks like 13 is going to be okay. Because if we sub in on the left side, you get 13 minus 5, which is 8. If you sub it on the right side, 5 times 13 is 65, minus 1 is 64, square root of 64 is 8. So you get 8 on the left, 8 on the right. Good, those are the same, so that works. But with 2, you sub in 2 on the left, you get negative 3, right? It's 2 minus 5. You sub in 2 on the right, you get 5 times 2 minus 1 under the radical. So that's a square root of 9. But the convention is to take the positive square root, so that's 3. 3 and negative 3 aren't the same number, so that one doesn't work. So 2 is extraneous here, and the only solution, the only real solution, is 13. So that's why you got to do the check, because things that look like they work may not actually work. Number 2, nice and short. Part of that is because we have an odd root, though. Where we've got a cube root, it's already by itself, so you say, okay, fine, we got a cube root, I want to get rid of that cube root, I'm going to cube both sides. Okay, that's the step. You do that, then on the left you're just going to have x plus 9, and on the right 2 cubed is 8, and then if you subtract 9 from both sides, you get that x is negative 1. Alright, and then to check just to make sure, even though since this is an odd root it'll be fine, but you sub in a negative 1, then you got the cube root of 8, which is 2. That's what's on the right side of the equation. So yes, this works. So x equals negative 1 is a solution here. Example number 3, what's different here? Well, you've got to get the root by itself, for one thing. Other than that, it's a fourth root, but that just means you got to raise both sides to the fourth power. That's a little bit different, but I think you can see it coming. So the only new thing here is you got to get the root by itself. Okay? Subtract 1 from both sides, you end up here. Then we've basically got things that look like the last page. Where then if you raise both sides to the fourth power, which is what I did right here, then on the left that's just going to be x squared minus 9, but on the right that's 2 to the fourth, which is 16. And if you add 9 to both sides, get the x squared by itself, you end up here. But if x squared is 25, use the square root property, then x could be positive 5 or negative 5. And then we got to check them both. So if we check x equals 5, so I subbed a 5 in on the left side of the original equation, we end up with 5 squared minus 9 under the radical, so that's a 16. But the fourth root of 16 is 2. You add 1, you get 3. Okay, great. That's what's on the right side of the equation, so that works. Negative 5, same idea. You sub in the negative 5. Once again, you're going to get a 16 under the radical, so the fourth root of 16 is 2. Add 1, you get 3. That also works. So they both work, so they're both going to be solutions here. The last one, number 4, it's written with a rational exponent instead of a radical, but you do about the same thing still. So if you still think, I want to get rid of that root, because then really if you think about that as there's a square, but there's also a cube root, you think, I want to get rid of the cube root. So I'm going to cube both sides. Okay, well if you do that on the left, you're going to have x raised to the power of 2/3 times 3, but 2/3 times 3 is 2. So that's x squared. Then on the right, this is kind of a big number. When you cube 16, you get 4,096. But then when you use the square root property from here, the square root of 4,096 is 64. So this is plus or minus 64. And then we got to check them both. All right. Well, let's see. 64 to the 2/3. The cube root of 64 is 4. You square it, you get 16. Great. That's what's on the right side of the equation. 64 worked. Negative 64. All right, sub that in, you take the cube root of negative 64, that's negative 4, and you square that, you get 16. That one works too. So 64 and negative 64 are both going to be solutions here.